Thank you very much for calling me to this meeting. Today, I would like to talk about lunar pickup ion, mainly observation results by Kaguya. I would like to introduce a recent result to discuss how to use pickup ion observation for lunar planetary science. This is the history of observation of pickup ions. It's a bit easy to follow this study because there are not so large number of paper and spacecraft observation. First, window spacecraft found heavy ions during the flyby operation, which mainly consisted of oxygen ions and aluminum ions. And then next, lunar orbiter Kaguya and Chang'e performed continuous orbiter observations. And then Ladi and Artemis followed these observations. Similarly to the lunar exospheric particles, a variety of ions, pickup ions, are also emitted from the lunar surface and observed by the INSS ion spectrometers. From here, I briefly present the introduction regarding lunar pickup ions. This slide shows the source mechanism of lunar ions. Source mechanism is very similar to the lunar exospheric particles. And now we know there are alkali exosphere around the moon and noble gases, which are founded by ground-based observation and spacecraft observation. And some of the exospheric particles are continuously photoionized and then become the pickup ion. In other cases, ions are directly emitted from the lunar surface. There are four source mechanisms which are the same mechanism as that of lunar exosphere. And my question is the last sentence. Can we derive any information on the moon from the pickup ions? For this question, source mechanism is very important. So now I'm trying to investigating this question using the Kaguya observation data. And this slide shows the motion of the ion emitted from the lunar surface and the exosphere. And their characteristics is here. Initial energies are almost negligible, and thus they are in so-called pickup ion motion. They are in the very large energy range, having up to twice solar wind velocity. However, when lunar orbiter observes such kind of ions at low altitude, their Raman radius are relatively large, so lunar ions just move straight along the electric field, as shown in this left figure. In case of Kaguya observation, lunar ion acceleration by electric field are up to a few hundred electron volts, not so large. From this slide, I show observation result of lunar pickup ion by Kaguya spacecraft. The left figure is ion energy mass spectrometer, which provided very good data for 1.5 years, this period. And this is an example of Kaguya observation data. Left panel shows one-day plot one-day plot of electron and ion and magnetometer. The right panel shows the energy flight time diagram derived from left one-day plot. We can see intense solar wind component. The most intense one is due to the solar wind proton. And the next one is caused by the alpha particles. We can see very tenuous low energy component here. These ions are from this ion, the lunar ion coming from the lunar surface or lunar exosphere. The bottom panel, this panel shows the flight time profile derived from the upper panels, only using the low energy components. We can find several ion species, including sodium, potassium, oxygen, carbon, and argon, and so that. So in the Kaguya observation, the altitude is 100 kilometers, so it's easy to trace back their trajectory to the originating point, as shown in this left figure. Then, using all the data from Kaguya, we have built emission map for several ion species like this. This map is plotted on the geographical coordinate. So the center area are the near side. And now we are expecting these maps would have some information regarding moon and lunar surface material. And then we are now analyzing the data and comparing the other observation result by different instruments and different spacecraft. From next, we discuss how to interpret this Kaguya observation result. Currently, we divide lunar pickup ion into 3 categories. First one is noble gases, which is probably provided by outgassing from lunar interior and radioactive decays. Some helium is brought by solar wind. Neutral particles of noble gases were successfully measured by Radi. Kaguya also measured helium and argon ion, but I have not yet obtained good science about these noble gases. So today I skip this topic. And second group is volatile, including alkali sodium and potassium. According to the study of lunar exosphere of alkali atoms, now we know their dominant source mechanism is photon-stimulated desorption. Because of their volatility, they are preferably dissolved. So the point is this source mechanism is effective only extreme surface. So now we suspect the volatiles do not reflect the surface material composition. And the third group is reflectories, including calcium, magnesium, iron, and silicon. It's difficult to emit this kind of elements, but the solar wind sputtering can emit everything. So this means the emission of reflectories may reflect the composition of the surface materials. Of course, we are now searching water ions, but we have not yet good data. So I also skipped the water issue. From next slide, I will show the observation result about regarding the two groups, volatile and refractories, in detail. This is a brief summary of lunar alkali exosphere, maybe presented by the previous Karen-san. But now we believe solar photon dominantly emit alkali atoms. And this emission process is very weak, so it emits not surface material strongly connected with surrounding elements, but that slightly connected with sort of lattice defect. Kaguya also observed this kind of ions, pick up alkali ions from moon, and found an additional feature that is dawn-dusk asymmetry, like this figure. From the Earth's ground, we can see good symmetry in north-south distribution, but INST observation clarified this kind of asymmetry in dawn-dusk distribution, as shown in this Kaguya observation results. And to explain this asymmetry, we made a model in which alkali storage in extreme surface dry up during daylight time. And our model estimated that 50% of extreme surface storage is lost during one day. But because the moon maintains alkali exosphere today, so 50% loss amount should be refilled during noon or night. Then we have one candidate for refilling mechanism. That is Micrometeoroid. We have not yet no direct evidence, but in our estimation, total loss amount of alkali atom and supply to the moon by micrometeoroid are very comparable, like as shown in this rectangle. These values are very similar. So this micrometeoroid can be one candidate for refilling process of the alkali elements. Anyway, we should take care. Volatile elements, especially alkali elements, is not only lunar origin, but also extreme supply, such as micrometeoroid. And next case is volatile carbon ion observation. Maybe 10 years ago, all we believed there was no carbon in the moon because such volatile elements were fully lost during its birth event, giant impact. However, Kaguya found carbon ion emission, and we obtained emission map like this figure. And it should be noted, magnetic anomalies disturb ion emission, so there is a very good anti-correlation between this emission map and the magnetic anomaly map in the right corner here. And this figure shows the good anti-correlation between magnetic anomaly and measured carbon ion fluxes. And our estimation shows the younger male carbon yields in the younger male areas are a bit larger than that in the older highland areas. This is one of the features. First, because carbon is a volatile element, we suspect origin of the observed carbon ions. First, we estimated supplies by micrometeoroid using the observation data and data derived from the model. And our estimate shows the supply by micrometeoroid is clearly smaller than the emission yield. So this is one of the results. And next, we estimated carbon ion supply by the solar wind using these observation data shown here. And our estimation also shows the supply by solar wind also smaller than the emission yield. So we conclude carbon ion emission. So next slide. We concluded carbon ion emissions are partly provided by exterior supplies, but some carbon was definitely embedded at its formation and or was transported a billion years ago. So this result means the giant hypothesis of the moon should be modified from current simple model, so-called volatile depleted dry moon, to another moderate mechanism, another moderate model, which allows a volatile contained situation, so-called wet moon. Then we go to next topic. This is the last group, reflectories. And now we expect pickup ion observation can be a natural CMS analysis for small bodies. Solar wind ion can play a role of a primary ion beam. So secondary ion observation may teach us composition of small bodies, similarly to laboratory CMS analysis. Several laboratory experiments show the solar wind ion possibly emit secondary ions, which reflect composition of the target samples using a ratio to silicon ions. Then there is some estimation by using laboratory experiment data and model calculation. And their estimation shows the observation of refractory ions can be useful for classification of targeted small bodies. It can discriminate between the formation models such as asteroid capture and giant impact. This figure shows the secondary ion yields from the several sources of samples. There, we can see clear grouping can be done for the several sources of meteoroids and several sorts of meteoroid. So Kaguya observation provided a good data set of emission of such refractory ion species, like this figure. So we can compare Kaguya observation data and estimation shown in the previous slide. The next slide shows this is it. We put one dot here on their estimated figure. And this result shows we can tell that the Earth's moon was made by a giant impact. The moon is the lunar materials is evolved materials. Of course, we have already know it, but the point is pickup ion observation can be useful for classification of unknown small bodies. So now we currently plan to do such kind of observation for Martian moon in the next MMX mission. MMX is JAXA's mission, which will conduct several sorts of observation and sample return. Then, okay, and this is next is the last slide. This is summary. I only listened to Kaguya observation result, and I shown the result using three categories: volatile sodium and potassium, and volatile carbon, and refractory ions, like this. Almost all of today's topics are published, but last two topics are still in preparation. Thank you. This is all.